condition variables enables the thread to control the proceed and block of other threads. If you use a mutex, if you try to use a mutex locks to do the same job, it will be impossible. It will be very strange and even impossible to do so. So let's try to design such a structure using a mutex lock, using mutex locks. So let's assume that T2 signals T1 to come to T1 blocks until T2 signals T1. So first we have to let T2 acquire a mutex lock, and then we need to let T1 call lock so that it blocks, and then we need to execute some stuff on T2 so that before it sends the signal, which is unlock the mutex lock so that T1 can continue, and then T1 does some stuff, and then it unlocks so that the lock is returned to T2, and it may lock and begin another loop. So we'll wrap this in a while loop, in a while true loop. This as well. But you can see that these two basically have the same structure, and all the thing that T2 can send the quote-unquote signal to T1 is that only relies on the fact that T2 acquires the lock before T1. If T1 acquires the lock before T2, then our structure is completely ruined, and no matter how you switch the order between these three components, like the essential problem still remains there, that which is that if T1 acquires the lock before T2, then it won't work. So that's why you can use a mutex lock to do the job for a condition variable. So these conditions are the conditions for a deadlock, also known as the Kaufman conditions. So the implementation of the POSIX library's mutex lock already ensures that there is mutual exclusion, such that the other thread cannot touch the lock M1, and no preemption, which means that there's no way for T2 to break this mutex lock. These are all implemented in our pthread mutex lock, and Holden weight is such a condition. So we first let T1 and T2 acquire their own locks. This is holding T1 and T2 holding their own locks, and we ask T1 to acquire the lock already acquired by T2, which results in waiting for T2. So that is hold and wait, and a circular wait happens when we add another acquired to M1 here, which creates T1 waiting on T2 to release M2 here, and we have T2 waiting for T1 to release M1. So that is so that you can see that there is a circular way here, which implies that these will cause a deadlock to happen, which it actually does. And for the reader-writer problem, we have first we have a data structure and some several threads. We call them the reader threads. It reads from the data structure without changing its contents. And there are also writer threads that updates its contents. And the goal for the goal for us to solve a reader-writer problem is that we need to use mutual exclusion and others and other controlling components such as conditional variables or semaphores and stuff, to make sure that there needs to be mutual exclusion between a reader and a writer, because we don't want a reader to read corrupted data that is currently updating by the writer, and we don't want two writers updating the data structure at the same time, which will obviously cause a racing condition. However, we do want multiple readers to be able to share the data structure, because there is no change to the data structure, so we don't have to prevent them from sharing the data structure. So that is the basic idea of the reader-writer problem. A critical section problem is that we have a critical section similar to the data structure we talked about in the previous problem 8. We have to design an algorithm that prevents that satisfies these conditions. So first it has to satisfy mutual exclusion, which means that multiple threads cannot. So if one thread is currently working on the critical section, other threads cannot. They must wait until the first thread finishes its job with the critical section. Then it can continue. And progress, I'll explain. Progress means that if a thread should check if there should do a simple check each time it executes, so that if there's no other thread accessing the critical section, it can simply proceed with the critical section. So one example is this one in the book. So basically it uses a common variable called turn, and so a thread waits until the public variable is the shared variable turns to its ID, then it does stuff to the critical section, then it sets the turn variable to another thread's ID. This will not work because the first thread will not access the critical section with a thread without explicitly being told by another thread by setting the turn ID to proceed. So one example is that one scenario is that the first ever thread that executes with these commands will stuck forever because there's no threads before it to set the turn to its ID. And a bounded wait means that like after a certain amount of time, any thread will get the chance to access the critical section. For example, if this let the thread with if I basically let the thread with a larger thread ID pass, it satisfies mutual exclusion because we resolve the conflict between two threads accessing the same critical section, but it is not a valid solution to this problem because like if you have a thread with a really large thread ID, it is possible to infinitely loop, and it will infinitely possess the critical section as well. That is why that is an example of progress. So these are the three conditions to satisfy for a solution to the critical section problem. My favorite part, and also the most challenging parts of cs241 is the multi-weak MPs. I think that they are most challenging because they have the most code to write, and it tests everything we learned from the courses. However, I think I learned the most from from the multi-week MPs, because not only do we refresh our memories with codes that use the knowledge from the courses. We also can write applications and infrastructures and logics with the knowledge and with those knowledge we learn from the course. So I think with those codes I write help me a lot when in understanding those materials.